All right, good morning, everybody. Today I'm going to go over page 381 and 382, 77, 78, 80, and 82. You probably found these problems the most challenging out of all of these problems so far, mainly because these are the word problems. Most of them weren't too difficult to complete. It's more of just the challenge of understanding what they're asking you to do. So let's get started. So number 77 was a monthly payment. And they gave you this equation right here. T equals 16.625 times the natural log of x divided by x minus 750, and where it says x has to be greater than 750. And what this equation does is it approximates the length of a home mortgage of $150,000 at 6% in terms of the monthly payment that you make. So in the model, T is the length of the mortgage in years, and then X is the monthly payment in dollars. And so what this is saying is you have to make a payment bigger than $750. So if your payment is just like, let's say 751, it's going to take you T amount of time to pay it off. The larger that you make X, the smaller T is going to end up being. And so looking down through this problem, the first thing they wanted us to do was use the model to approximate the lengths of a $150,000 mortgage at 6% when the monthly payment is $897.72. So this $897.72 is what you need to plug in for X right there and right there. So this is definitely a calculator problem. And so I'm going to see if I can minimize this and see both the problems. Looks like I can, roughly. We have 16.625 times natural log of, and then the first payment they want us to look at is 897.72 divided by, now we're going to need a second set of parentheses there, 897.72 minus 750. And then we need to close both of those parentheses out. And when I hit enter, you can see almost on the dot, if you make a payment of $897.72, it will take you 30 years to pay off a $150,000 mortgage. They also want to know uh, how long it will take you if the monthly payment is $1,659.24. So if you hit second enter, it'll bring up your last entry, and then we can simply go in here and change this number. You are going to have to insert one digit since the new payment is one extra digit. You're going to hit second insert, and then you can type your 1, and then the rest of it is going to be 65924. And it looks like it inserted it all there, so we need to delete all that. And same thing here. We're going to hit second insert, 1659.24, and we're going to delete the rest of this. And there we go. Everything else is going to stay the same. Hit enter, and you can see that you will pay $1,659.24, but you will only pay for 10 years versus 30. Now, the second part of this problem says approximate the total amounts paid back over the term. And so what we need to figure out, and this is very similar to what you guys did on your packet. In fact, it's almost exactly the same, is we want to find the total amounts paid back over the term. So if we want to find the total amount paid back for the 897.72, 897.72 is paid for 30 years and every month. So we take 897.72 times 30 times 12, and that shows you that you're going to pay $323,179.20 back on your original. If you remember, the original mortgage was for $150,000. You'll pay $323,179.20. Similarly, if you want to figure out how much you're going to pay back when you're paying $1,659 a month, you're going to take 1659 and 24 cents. You're going to multiply that by 10 years, and that still needs to be multiplied by 12 because you're paying once a month, and you will only pay back $199,108.80 if you pay your mortgage back in 10 years versus 30. So quite a significant amount of savings if you can swing the much larger monthly payment. So that was part B, approximate the total amount paid over the term. Now, part C wants to approximate the total interest charges for each monthly payment of $897. And as we said, if you want to know the total interest for the first one, you're going to take this number. I'm just scrolling up with my up key. I hit enter, and then I put minus 150,000 since that's the original amount of the mortgage. And you can see in the first scenario where you take 30 years to pay back, you will pay back $173,179.20 in interest. Then they asked for the total interest for the $1,600 a month payment. So we will take the 199 and subtract away 150,000 for that one as well. And you can see you will only pay $49,108.80 in interest if you pay it back in 10 years versus 30. So it's at least 3 times more expensive to take it out to 30 years. Now it says, what is the vertical asymptote for the model? Interpret its meaning in the context of the problem. This one, I'm just going to tell you what it is because we've not really discussed rational functions yet. But the vertical asymptote in this model is going to be 750. And the reason why it's 750 is if you plugged in 750 for x right here, you would get 750 minus 750, which would give you a 0 on the bottom of this fraction. When you get a 0 on the bottom of a fraction, that actually creates an asymptote. That's why it says x has to be greater than 750, because you don't want to have that asymptote. And so this part D, what is the vertical asymptote of the model? It is when x equals 750. Its meaning it is when the bottom is, when x is 750, it gives you a 0. And you would actually, in the problem, it means you would never be able to pay that money back because the interest is exceeding your monthly payment, which is not a good thing. All right, so that was number 77. That was quite a long problem. Let's look at number 78. The percent P of households in the United States with wireless-only telephone service from 2005 through 2011 can be approximated by the model. You can read the model P equals -4 plus 1.335 T times natural log of T, where T is between 5 and 11. T corresponds to a year, and T being 5 corresponds to 2005. And they want you to complete the table. Now, as I've shown you earlier in the year, anytime you have a table, the easiest way to complete that table is to use the table function in your graphing calculator. The way that you do that is you go into, press your y equals key and get your y equals screen up and put in the equation. So you can see I have -4 plus 1.335 x times natural log of x. And they want to fill out the table from 5 to 11. So if you hit second table settings, which is the window key, we want to make sure see right now my table's starting at -4. Everybody's might be starting different. We want our tables to start at 5. So change that to 5. And we want our change in the table to be by ones, and we want it to automatically generate. So you want both of those to say auto. We may have changed the first one over to ask at some point. So make sure this is set to 5, 1, auto, and that was second window. Once you have your table set up correct, go ahead and hit second graph, which is the table, and you can see we have all the values to fill out the table. Now it says using a graphing utility to graph the function. So if I just hit, so we already have the equation in for y1. If I just hit zoom 6, you're going to see a graph. And it's pretty good. I don't know that we actually need to mess around with that too much. If you really wanted to, based on the table going out to 11, you could adjust the x-axis a little bit. So we could actually make this table go out to, we'll go out to 12 just so we can see a little further. The y-axis is going to need to be a lot bigger though. I would actually make this into 100 and change this to 10. So if you take a look, I changed the x max to 12. I changed the y max to 100 and then the y scale by 10. And what that's going to let us do, go ahead and hit graph, is that's going to let us see a full picture of the graph as it's rising across from 2005 to 2011. So that was part B. It says use the graphing utility to graph the function. Part C says, can the model be used to predict the percents of households with wireless only telephone service beyond 2011? And it says explain. So the short answer is no. And the reason why is this says the model is only accurate for 2005 to 2011. However, if you wanted to go beyond 2011, you could look at it. All you would have to do is go to your window and change your X max. Let's change it to 20. And I'll change the scaling to 2. That way you're going to not see too many hash marks. And so I changed the X max to 20. And by doing that, I'm going to be able to see further out on this graph. And so even though the restriction on this model says it's only good from 2005 to 2011, and this only accurate for that, you could use it. So it's kind of a yes and a no question. All right, so that's number 78. Now looking at number 80, that's on the next page, so I got to close this out for a second. Here's number 80, another compound interest problem. It says a principal, P, is invested at 5.5% and compounded continuously, increases to an amount K times the original principal after T years, where T is natural log of K divided by 0.055. And it says complete the table and interpret your results. Sketch the graph of the function. So this one, much like the last one, can just be completed using your graphing calculator. It's pretty straightforward. We're going to go into the y equals key. We are going to type in natural log. Instead of K, we're going to use X, divided by 0.055. We're going to hit enter. This time our table's starting at 1. It's going 2, 4, 6, 8, 10, 12. So I'm going to go back into my table settings. I'm going to start my table at 1. Everything else I'm going to leave alone. I'm going to click on table, and you can get the values that you need. You need to go up to 12. So once you get the other values, you can simply scroll down and get your last value, which is 45.10. Then it asks you to sketch a graph of the function. That can be easily accomplished by simply hitting zoom and then 6. And there's a graph of the function. If you wanted to zoom out a little bit, you could to see a little bit more of it, but I'm okay with that as well. The last one that I asked you to complete from this homework set was number 82. And this is a problem about sound intensity. Earlier in a lecture, I mentioned that logarithms are used in a couple different places, and I mentioned the Richter scale as well as the pH scale in chemistry. Another place that is used is in the intensity of sound, which is measured by decibels. And you can see this beta, this B with a tail is called a beta. And sound decibels are also a logarithmic scale. And so whenever you go from like a 60 to a 70, it is a lot more significant than you think because it being a logarithmic scale. It's not just a straight linear scale. So it says the relationship between the number of decibels, beta, and the intensity of a sound, I, in the watts per square meter is beta equals 10 times log of I over 10 to the negative 12th. It says determine the number of decibels of a sound with an intensity of 1 watt per square meter. So the intensity is 1. So we're going to plug a 1 in right there. So we're going to get our graphing calculator. We're going to go into the home screen, and we're going to type 10 log, and then we're going to have 1 divided by 10 to the negative 12th. And you got to make sure you get down out of that exponent place before you put in your parentheses, or else you'll get an error. And when you click that, you can see that the decibels would be 120. Part B asks you to determine the number of decibels of a sound with an intensity of 10 to the negative 2. So that's a much smaller number. So I can actually hit second enter, bring up the entire thing that I already typed in, and then just go right over here and type in right after the 1. I'm going to hit second insert again, and I'm going to make that a 10 and make it to the negative 2. So you can see I have 10 to the negative 2 divided by 10 to the negative 12th. And when I hit enter, you can see that the decibels are reduced to 100, which is still extremely loud. Part C, the intensity of the sound in part A is 100 times as great as part B. Is the number of decibels 100 times as great? Explain. And this is what I was talking about before I started this problem. You can see that the difference between the decibels is 20. So you go from 100 decibels to 20 decibels. But what it is, it's 10 and then another 10. And because this is based on a logarithmic scale and not a linear scale, a difference of 10 and then another 10, those get multiplied, which is why it's 100 times greater. So every time you go from 50 decibels to 60 decibels, that's a 10 times greater. 60 to 70 is 10 times greater. And so it continues to build. So if you go from like a 60 to an 80, that's 10 times 10, which is 100 times greater. And so the answer here is the number of decimals 100 times greater? And the answer is no. The decibels are the number themselves are not linear. Therefore, this is not 100 times greater than this. All right, guys, that concludes me covering the 4 word problems I asked you to work on. So as always, if you have any questions, feel free to send me a message on Google Classroom or send me an email, and I'll do my best to help you out. Take care.